And then when you do all of that algebra there, you're going to end up getting 7 over 32, or in decimals 0.21875. And notice that this number is a lot less than this one. And also notice that this area, right, which is the area of these 4 rectangles that we just did, notice that this area is actually less than the actual area under the curve. Right, when we were dealing with these rectangles before, the first ones I drew out, remember the area was greater than the actual area under the curve because the rectangles were above it. They were all above the curve. Notice that these rectangles here, they're all below the curve. And so from here, what we know is that the area of the curve, the area under the curve, the actual area, which we don't know yet, but we definitely know that the area under the curve is going to be greater than this value here. Right, so it's less than this value, but it's greater than this value here. And that's always, that relationship is always going to happen when you're using these corners here. So when these corners are the right corners of the rectangles, that area is always going to be greater than the actual area under the curve. And then when the points here are going to be the left corners of the rectangles, that area is always going to be less than the area under the curve, the actual area under the curve. And so with all of this here, let me erase all this here. Let's put a little summary. What we can say is that the area under the curve is going to be greater than L4, the area of these 4 rectangles, but it's going to be less than R4, right, which is this over here. So bringing in these numbers, we can say we got 0.21875. And you don't have to work with decimals, but this example, like what we're going to be going through, is just easier to compare decimals sometimes than like more complex fractions. So the area under the curve basically has to be between this value and this value, right? It's going to be somewhere in between those. Is basically the summary of the work that we just did. Now, what's the problem though? The problem is that this interval here, it's actually quite large. Right? Between 0.21875, 0.46875, it's kind of a large interval. So like, where is it going to be? Is it going to be at 0.22 or 0.29 or 0.3 or what? Like, it'd be a lot better if we can have maybe something like the areas between 0.21875 and 0.21871, you know what I mean? Or something like that. Then we can really start getting more specific, right? But as of now, with just 4 rectangles, this interval is pretty large. We don't have a good approximation for the area under the curve yet. So the question is, how can we tighten up that interval, right? How can we get a better approximation? And the answer is we would have to use more rectangles. We would have to use more rectangles because the more rectangles you use, what happens is that this like excess area over here starts becoming smaller and smaller, right? So instead of drawing 4 rectangles, if we actually drew like 8 like rectangles, so if we added like sub-intervals over here and created these extra rectangles, then what would happen, notice that now some of that excess area is going to be filled in now, right? If that makes sense. So basically, the more rectangles that you're using to approximate, the tighter this interval is going to be. And so the more precise now we're going to get to that actual area under the curve. And let's actually illustrate that. So let's, instead of using 4 rectangles now, what I'm going to do is I'm actually going to use 5 rectangles. So we're going to go through the exact same process, perhaps a little bit quicker. But instead of using 4 rectangles now, I'm going to be using 5 rectangles. So what I'm going to do is I'm going to draw out y equals x squared from 0 to that x value of 1. But what I'm going to do now is instead of splitting up into 4 subintervals, we're going to split it up into 5. So let's try to keep it 1, 2, 3, 4, 5. So maybe not as to scale, but nevertheless, this is what we got. And then this one, it's like 5 over 5, if you think about it. All right, 1, 2, 3, 4, 5 over 5. Right, so if we take 0 to 1, split it up into 5 subintervals, we got x values of 1 over 5, 2 over 5, 3 over 5, 4 over 5, and then 5 over 5, or 1. And so what I'm first going to do is I'm going to create an expression for R5. Right, so 5 rectangles, but because this is an R here, what we know is that each of these points here, they're going to be what? They're going to be the right upper corners of each rectangle. So the rectangles are going to be like this, and then we're going to have this, and then we're going to have that, this rectangle, and then that rectangle up here. So notice the area of these 5 rectangles, it's going to be greater than the area under the actual curve, as we know, as we've mentioned. Right? So what's this expression now going to be? Well, what's the length of this rectangle going to be? It's going to be 1 over 5. What's the height of it going to be? Well, it's going to be the height of this point, which is just going to be f of 1 over 5. And the function that we're actually dealing with is x squared. So this is going to be like 1 over 5 to the power of 2. So this is going to be 1 over 5 to the power of 2. So this here represents the area of that first rectangle here. And then we're going to follow the same pattern. The length of all of these rectangles is going to be the same. It's going to be 1 over 5. What's going to be changing is the height of each one. So over here, we're going to have 1 over 5, the length, times the height, which is going to be the height of this point, which is going to be 2 over 5 to the power of 2. Then we're going to have 1 over 5 times 3 over 5 to the power of 2 plus 1 over 5, 4 over 5 to the power of 2 plus 1 over 5. Just keep it consistent. Instead of writing 1 to the power of 2, I'm going to put 5 over 5 to the power of 2, just so you see the pattern of these x values here. So instead of writing 1, let's just write this as 5 over 5.